go ahead and start the class. Welcome to aerodynamics. EMCH 578, 4744. These are the course syllabus that I have put on Blackboard. I just wanted to make sure that everyone has the syllabus. Already 5:30. Let's go ahead and start. My name is Mustafa Mobli, and this is aerodynamics. Welcome to 2021, I guess. Today we are going to have some small introductions about me, who I am, about the course. We will go over the syllabus that I've printed out for you guys. I will talk about my expectations. I will ask you about your expectations. We will talk about the class goals. We will cover the semester topics. And then we will go over some historical perspective. And if you have the time, we will begin the introduction chapter of the course, of the class. Is there any questions before we start? No? Okay. So, let's talk about the syllabus. I assume all of you already have the syllabus in front of you, so let's go over it from here. Before I begin, this is a cross-listed course, so some of you have registered for EMCH 578, some of you, or graduate students, should have registered for EMCH 744. The graduate student section is also cross-listed with an online section. That's why we are recording the lecture. So graduate students, there are some graduate students who are online right now, or should be online right now. There's only one. So just so you know, the recordings, I can make the recordings available to all of you after the class. So it won't be live streamed for undergrads, but you will have access to recordings after the class. So let's just start. Let's go over the course syllabus one by one. This is the aerodynamics, as I said. In this course, you have to know a little bit of calculus, integral calculus, and differential equations. There is no official prereq for the course, but the expectation is that you already know the mathematics behind it, and a little bit of fluid mechanics. We will reintroduce whatever concepts we want to talk about in this course, but you are expected to at least hear the names of the things that you want to discuss, okay? And as I said, my name is Mustafa Mobli. My information is listed here, my email, my office number. The office hours are going to be Mondays, 3:30 to 5:30 p.m. You can come by my office anytime. The door should be open. I usually have headphones on, so I may not hear if you knock on the door. If you knock, I didn't answer, just open the door. And hopefully I'll be there. Yeah, it will be online. If you had any questions outside of the office hours, send me an email or call my office. I usually reply to emails very quickly. You can actually come by my office as well, whatever you like. My office is in the same building, Wing A, room 117. Is there any questions about the office hours or the meeting times? Okay. The textbook for the course is The Fundamentals of Aerodynamics by Anderson. It is a very famous textbook for aerodynamics in general. This guy actually has a lot of other aerospace related books as well. And this is going to be our main textbook. I will use some material from other textbooks as well, but I will send you the PDF files or create handouts for you, so you don't need to purchase any other book other than this. I'm pretty sure you will be able to find a PDF somewhere online as well, but it's a very famous book. What else? Meeting times of the class: Mondays, Wednesdays, 5:30 p.m., 6:45 p.m. I know it's a little late, I don't know why they have scheduled the class this late, but it's been like this for the past 5-6 years. So sorry about it. And any questions so far? No? Okay. So let's go to the assessment first before moving on. The grading policy. As I said, we have two groups of students here, undergraduates and graduates. Of course, I expect more from graduate students. I think that's given. But homeworks and exams are essentially the same for graduate students and undergraduate students, except for some extra questions of the exams that the graduate students will get, but the policy is going to be the same. You have to submit your homework at the beginning of the class. If you cannot make it, send me an email. If you talk to me after the fact or after the deadline, you'll get a 0. So if you cannot make the deadline, just send me an email before the fact, okay? And then we'll try to work something out. The examination, we have 2 midterm exams. You will get 1 hour and 15 minutes in the class time for the exams. If you have registered with SDRC, the Disability Services, they have different policies. And I'm pretty sure I'll be in touch with you after the class or in this week. But for everyone else, you will get 1 hour and 15 minutes for 2 midterm exams, essentially. And we will get 2.5 hour final exam. The final exam will be comprehensive, of course. Is there any questions so far about the exams? If you feel like I'm rushing through the syllabus, just let me know. I'll try to go a little slower, but I think there's nothing out of regular here that I need to slow down for. So, what happened? Yeah. Yes, example. I usually let you guys have your books, notes, and whatever in the exam. But you cannot use any computers or tablets or solutions to the problem, because sometimes I use like homework problems that I've already given you in the homeworks in the exam. So you can bring your books, or I don't know what I've said here though. Yeah, I haven't mentioned anything. But it depends on the exam. Of course, if the exam is open book, it's going to be a little harder compared to closed book. But we can discuss these policies, these things before the exam, whatever you guys prefer. The midterm exams will be held in the regular class time. We have pop quizzes that won't be graded, but will be used as attendance check. But your presence in class is not mandatory. So how does that work? If you don't come to class, you can talk to your friends or classmates, get the quiz from them, and just submit an answer. It doesn't need to be the right answer, but just to see some work. I just need to see some sort of participation in class activity and like whatever we discussed, okay? But submitting the pop quizzes is like 5% of the grade, if you're going to see later. There won't be any late or makeup work, as I mentioned, unless you have already talked to me, and the grading scale. For undergrad, the pop quizzes will be 5% of your grade. Homework will be a total of 20%, 4% each homework. Exam 1 will be 20%. Exam 2 will be 20%. The final exam, which is going to be a comprehensive exam, is going to be 35% of the total grades for a total of 100%. Graduates, how many graduate students do we have right now? Okay. 5 students, okay. Graduate students, pop quiz 5%. Homework is going to be only 10%. Exam 1, exam 2, and final are going to be 20%, and your project is going to be 25%. If there's any one of undergraduates who wants to do a project, you are actually encouraged to do so, and you will be treated as a graduate student when it comes to grading, okay? And we will talk about the project a little bit later. Let me just finish the syllabus first. The topics we're going to cover is a little bit of fluid mechanics background. Then we will move on to invisible incompressible flows, airfoil, and wing analysis. And this part of the class is going to be depend on the time, and I may actually replace it with fluid mechanics. So it is going to be either compressible flows, viscous flows, and elements of hypersonic flow, or fluid mechanics, or nothing if we didn't get to teach the material. Because of the COVID situation, I assume you guys understand that nothing is set in stone. Okay. And there are learning objectives or outcomes of the course on the syllabus. The expectation from you going out of the course is this is second page of the syllabus. Yes. There are 3 outcomes that you're expected to know when going out of the course, and hopefully we will reach all of those outcomes. This course is a little heavy on mathematics, so hopefully your problem solving and analysis capabilities will be improved at the end. I know when it comes to mathematics, it becomes a little scary for a lot of you guys, and I'll try to help you as much as possible, and we'll try to solve as much example problems as possible as well. I'm also available outside of the classroom, so whenever you had any problem, come to me, talk to me, and ask your questions, right? Okay, and hopefully you'll learn something for the rest of your life. Yeah. Any questions so far? I don't know what is happening, so I'm sorry about this. It's just random noise. What are my expectations? My expectation for you guys is to come to the class prepared. If you can read the book, make sure to go ahead and read the book before coming to class. If not, that's all right. Just glance over the lecture notes that I'm going to post. I'll try to post all of the lecture notes before the class, as I did for this class. All of the lecture notes for chapter 1 is already posted, so you can print them out and come to class prepared actually. And then coming to class is of course important. And in general, when I know you, when you ask questions and when you participate, it usually will have a positive, and it's not about me, it's a general thing, it's about any of your instructors. When we know you guys, then we will have a more positive attitude when it comes to grading or giving you the final grade. So it's going to be benefiting you when you participate in class, right? You learn more, of course. You can ask about your problems, and then it will be a positive impact on your teacher. So yeah, participate in class. Participation is very important to me. Be honest and professional. Don't cheat. If you don't know something, if you don't know the answer to a homework problem, come and ask me. We'll try to solve it together, but don't cheat. Of course, you can find I'm pretty sure you can find a solution to most of the problems I post online, but the purpose of the homework or exams is not for you guys to get an A, it's for you guys to learn. So if I see you are not learning, I try to not give you the answer, but I try to help you find the answer. Okay? Any questions so far? No? Yeah. What are your expectations from this class? Let's actually start from there, and you go one by one. Okay, fair. You don't have to have an expectation. I just want you to say something.
I guess mine is just a question. How strict are you generally when it's showing work on the exams?
What do you mean by showing work?
For our questions, is our work with the answered grade, or how does that work?
Like the procedure?
Yeah.
Yeah, that's very important. That's 95% because that's the part that shows your understanding of the material, right? That's it? Okay.
I guess mine would be a bit more like understanding of how air flows. Just basically this.
Okay. That's aerodynamics, right?
Yeah.
Honestly, I don't have any expectations for you, but I guess I would say you can't help aircraft and airplanes function. So.
Okay.
I just started my master's in aerospace, so
So you had to take this, right?
What?
You had to take this course.
Yeah, it's also one of the first ones like that I take that's really strictly like aircraft and procedures in that sense. That's kind of my expectation is to like get an introduction to the field of aerospace.
Okay.
I've always been interested in aerospace engineering, so seeing if I enjoy learning about it.
That's good.
I'm not really well versed in aerodynamics, but I think it's interesting to learn about. So.
Makes sense.
Mostly, I don't know anything really about it. I mean, I know like basic stuff, but I forget the details, but I can learn about that.
Okay. You don't have to talk about your expectation from this specific course, but your expectation from your instructor or whatever your expectations are when it comes to class. Okay. So, yeah. Makes sense.
I'm expecting to get a better understanding of the mechanics of flight, basically.
Mechanics of flights. Okay. Okay.
This is my first course taking something to do with airflow, and I just want to come and learn.
You have had fluid mechanics, right?
Yes.
You too as well. Did you get your undergrad here?
Yes.
Okay.
Yeah, I just like to understand how fluid dynamics relates to aerodynamics, and I guess I would expect to like have the necessary resources if I had to miss for if I was positive for scenarios such as that.
Okay.
I just had fluid mechanics, and this is my first course related to aerodynamics. I said to myself, after finishing the course, to understand aerodynamic behavior of structure.
Okay. Makes sense.
Just always been interested in aerodynamics and just trying to learn as much as possible.
That's fair. Okay.
My bachelor's were in engineering, so I actually like use some skills that I've maybe about aerodynamics. I'm from outside the US, so I really do have cool background.
Okay. Yeah. Sure.
I'm kind of just looking to get familiar with that subject and not really know much about it.
With what? You want to get familiar with what? Aerodynamics, did you say?
Yeah.
Okay. Sorry. I can't hear you very well. That's all right. Yeah. Tell me about it. That's actually more exciting for me too. It is hard to design a take-home exam, honestly. It is very hard. Okay, that's fair. So I guess most of you don't have any expectations from me specifically, but you just want to learn more about aerodynamics, and that's what we plan to do here. So hopefully at the end of this, you learn more about aerodynamics. But the next part is the introduction. You guys, I'm gonna introduce myself first, and then in more details, and then you guys will go ahead and introduce yourselves as well. I got my bachelor's at University of Tehran. It's a school located in Iran. I'm not sure if you're familiar with that country. Some people call it Iran here, the enemy country. So I'm pretty sure you have heard about it. Yeah, I got my bachelor's at 2012 at that university. Then I moved to the US. I spent some time in New York State. I moved on here. I got my master's here in 2014. I got my PhD as well here as well. in 2018, and I've been an instructor for aerospace engineering courses since then, since 2018. I liked it here, so I just got a job here. And I don't know what's going to happen afterwards. Hopefully, I'm going to stay here. That's the plan for now. My research is, I do two distinct research, actually. I do some advanced energy research, which is mainly means that I numerically simulate plasma discharge. Is there anyone who is familiar? I'm pretty sure most of you are familiar with what plasma is, or plasma discharge is. Yeah, I essentially numerically analyze those. Plasma discharge is very useful in a lot of fields. The field that I did work on was essentially aircraft analysis, or modules, devices that can reduce the flow separation on a wing, directly barrier discharges. We will see those a little bit. I will talk about those a little bit in this course as well. And then for my PhD, I was mostly involved with multi-phase heat transfer simulation, again, numerical simulation. So essentially boiling and condensation. That's it. That's it about my research. Have any questions or anything that you want to know about your instructor? No? Honestly, by chance. So I sent an email to a professor here. He was working on plasma research, and I was very interested. He offered me the position and came here. But the interesting part is that my wife has a bachelor's degree in plasma physics, so that was very interesting. And she changed her major after bachelor's, but so it is an interesting field, though. So you can talk to Dr. Farooq if you are interested in doing some research. Okay, so if you don't have any questions about me, let's talk about you guys. Let's just start from the back this time. Let's start from that. Introduce yourself. Tell me what is your major. I assume most of you are mechanical engineering majors, but I've seen some people from mathematics and physics department in this course as well. So what is your major? Are you a graduate or undergrad? What are your interests in life or in research? You can answer that third question however you want to answer. Now, let's go. You have to speak a little louder. What's your name? Michael. Okay. Mechanical engineering undergrad. What are your interests? Not being in class? Okay. Who do you work with? With Valve, okay. Oh, I haven't seen you though. Nice to meet you. Nice to meet all of you, actually. Go ahead. Utility design? Okay. Interesting.
My name is Harun.
Harun? Okay.
There's a company that does in general maintenance of rotating equipment, mostly steam and gas equipment.
So you're doing a master's here?
Yep.
Okay. Who are you working with?
Currently, I'm not working.
Okay, so you just came. Okay.
My name is Drew Brewer. I'm a senior mechanical engineering student.
What was your name again? I'm sorry.
Drew.
Drew?
Drew.
Okay.
Mechanical engineering senior. I'm interested in automotive manufacturing. I go off with automotive manufacturing digital.
Okay.
Around a year and a half. So I'm looking to, after graduation, get into automotive manufacturing.
I'm Fatima. Graduate student. I got my master in solid mechanics, and now I'm in vibration
Full disclosure, I've known her for a year. She has been my TA, so any conflict of interest, let it be out in the open. Go ahead.
Ryan, I'm an undergraduate mechanical engineering major. I'm also interested in the manufacturing side of the automotive industry.
Okay. Manufacturing. A lot of you guys are interested in manufacturing, which is, I guess that's kudos to Rami, right?
I'm Reese. I'm an undergraduate in mechanical engineering.
Reese?
Reese.
Reese, okay.
And for my interest, I'm not really sure yet, so I'm taking a bunch of different electives to kind of figure that out.
Okay. Makes sense.
I'm Ben. I'm a mechanical engineering undergrad with an aerospace minor. I'm interested in space, so I'm currently applying to a bunch of aerospace graduate programs.
Space. Have you tried the other USC, the fake USC? They have a very good space program, just space.
I don't think I could apply to that one.
Yeah, check that one out. Sorry, I've seen you two somewhere, but I can't put my hand on it. Or in a heat transfer class, right? Dr. Khan's heat transfer class.
Yeah.
Yeah. Okay. Yeah. Okay. Well, that's nice. Interesting.
I'm a mechanical engineering major, and I enjoy cars. I love to design cars.
It is actually, to be able to design cars, you have to know a good deal of aerodynamics. All right? Go ahead.
My name's Thompson. I'm an undergraduate mechanical engineering major here. I think I'm still trying to narrow down my interests. I think as of now, I'm probably around thermodynamics, especially with my senior design project.
What is your senior design project?
My group is like more exploring the way we're supposed to design the modular place system.
Interesting. Yeah?
My name is Wyatt. Undergrad mechanical engineer, and I really like physics and space, just in general. So that's my main interest.
That's cool.
My name's Matt. I'm a graduate student. My undergrad is here in mechanical engineering, and I'm doing aerospace engineering right now as my master's of engineering.
Who do you work with?
I'm working with Robin James and under Dr. G at the Williams Research.
Yeah, I know Robin.
Okay.
It's the guy with the face mask, right?
Yes. Yeah. And we're doing research in composite materials, so that's kind of where my interest is right now.
My name is John. I'm a graduate student for aerospace engineering, and I enjoy running for causes and have an interest in aircraft and design. National.
The target. Who do you work with? No one.
I'm Grace. I'm an undergraduate mechanical engineering major, and I'm interested in boat design and sailmaking.
Boat design. And what?
Sailmaking.
Sailmaking. Interesting.
I'm Cole. I'm an undergraduate mechanical engineer, and I'm kind of using electives to figure out my interests as well.
I'm Ty. I'm an undergrad mechanical engineer, and my interests are aerospace design. At least I'm trying to get into that, and possibly materials.
Okay. Interesting. I don't. I'm not gonna remember most of your names, of course, after the first run. But hopefully by the end of the semester, we will know each other a little better. So, and I'm sorry that you have to sit in the class. But, I cannot do anything about your interest. But I guess that's it for the introduction to the course and you guys. If you have any questions about the course policy, or we didn't go over the course schedule at all, but it is listed there, the exam times and dates, all of them are there. The homework, I forgot to talk about the project, the graduate. So how many graduate students did you have? 1, 2, 3, 4, 5. Okay, so you need to form teams, of course. Then you can either come up with a proposal for a project yourself. And there's a deadline for proposal submission. You have to form a team as soon as possible. Then you have to meet with me to talk about your idea for the project, or lack of an idea. I can give you the idea for the project. And then all of the deadlines that relates to undergraduate students are marked with a G at the end. So meeting for project is due by January 25th. So in essentially 2 weeks, right? So you have to meet with me before this time, and that will be a part of your project right as well.
Would that be someone on the online section next year?
I guess there are 4 people in the online section, but all of them are new, so yeah, I think so. Just have to get used to it. What was I talking about? Yeah, and your proposal is due, which is going to be a formal proposal. You have to write up the proposal, like 5 pages of proposal. It's going to be in February, and so on and so forth. So you have to form up the team as soon as possible. There should be 6 graduate students in the class for the face-to-face instructions, and we have 8 graduate students that are going to be online. So the same thing that I said to the people here is going to apply to the online students too. So make sure to form up the teams and meet with me over Zoom or whatever. And we can move it. And there are 5 homeworks, 2 exams. I guess that's it. And we covered essentially everything, right? I will ask again, is there any questions about the policy or anything? No? Okay. Let's go ahead and start. Let's start with the flight historical perspective. We, as human, as mankind or whatever you want to call it, we have been always thinking of flying, of course, and we have always looked at nature as inspiration for flight. Like birds have always interested us throughout the human history, and we always wanted to fly, as you have seen in many of the stories and myths that we have been like hearing and reading about for the past like millions of years or whatever, right? But one of the most famous stories about flying is the story of Icarus. Who is familiar with Icarus in this story? So most of you, some of you, like, who wants to elaborate on Icarus?
I think it's like a myth about a dude, a father and a son that built wings. I don't remember why, but the kid enjoyed flying so much he could because the son relaxed.
Yeah, they were supposedly the first engineers of the world, right? So they just designed things, and one of the things they designed was wings, right? they wanted to, I think Icarus is the sun. He wanted to escape Crete, which is an island near Greece. And he flew too close to the sun. All the wings burned down and fell down from the sky. So that's one of the earliest stories recorded about the flight. But then when you move on to the 16th century, the earliest designs, real designs and studies of flight appears in the works of Leonardo da Vinci. And Da Vinci actually was a pioneer in aircraft design. You can see it in the Da Vinci's ornithopter, which is this one. He was also a pioneer in helicopter design. You can see in the designs of the helicopter he has here. And he also was the first one who thought of a parachute. You can see the design. These are the original drawings, Da Vinci's drawings. He was a visionary, of course, because at the time the mechanics of it was not known. Even the mathematics that could find the mechanics of flying or flight was not known. So it could foresee the future. But the first ever recorded the first time ever that a flight was recorded was the Montgolfier's flight. So this balloon was designed by Montgolfier, and the principle was very simple. If the gas inside the balloon is lighter than air, it will go up, right? But they had no way of steering the balloon. It just went up, and whenever you turn down the heat, the gas became a little denser, and cooler, denser. It became heavier than air, then just came down, essentially. This was in November 21st, 1783. Then the first aerodynamic analysis appears in the early 19th century by Sir George Cayley in 1804. He was the one who understood the importance of angle of attack and the curved surfaces for the generation of lift, which is very essential for flying. And we're going to see later on. We're going to calculate lift for a lot of different conditions. His design had a fuselage, as you can see, had tail, and had also wings. He also proposed an engine for thrust, but the engineering at the time was not complete enough for a small engine to be designed and put on an aircraft. So they had to wait another roughly 100 years. Then we have the first glider flight, the real flight. This is essentially the first recorded flight that resembles an aircraft, which means that this is flying with all the principle of lighter than air. So you are actually heavier than air, but you can fly. And this is the glider flight, right? Otto Lilienthal. It was the first human. He was the first human that could fly with a glider. It was his own design. He actually crashed and died in 1896, but he had 2,500 successful flights before dying, which is a huge achievement for the first person who flies. Then we moved on a little further. Dr. Samuel Langley had the first successful airframe propulsion flight. So he essentially had the glider, put an engine on it, and then flew it. Okay. It was the first ever airplane that could fly with an engine, but it didn't carry any human. I'm pretty sure you know who were the first people who did design an aircraft which could carry a human. Wright brothers, of course, which flew their plane pretty close to here in North Carolina, Kitty Hawk, North Carolina. The interesting thing about the Wright brothers was that they've been working on their plane for, I think, 25 years, a long time. but their designs didn't fly, mainly because they relied on Dr. Langley's analysis for airfoil design, for the lift and drag coefficients, and all of those things. And Dr. Langley's designs for their specific airfoil was wrong. So they had to go back to Ohio, they had to redo all of the analysis, calculate the drag and lift coefficient. They actually designed a wind tunnel in their own garage, and they analyzed their own airfoils. They came up with their own charts, and then they designed a new airplane that could fly. It was the first ever human carrying flight recorded in 1903. Any questions so far? So a very short history of flight, and afterwards we had a very rapid progress of flying because aerodynamics as a science became more known. Essentially, people came up with the equations that govern aerodynamic relations, that govern like flying and movement of air over objects, essentially. You can see 3 examples of this progress here. We have the 1918s, just like 15 years after the first ever recorded human carrying flight. We have the aircrafts fighting in battle, First World War, right? This is a very remarkable achievement. Not in a peaceful direction though, but it is remarkable nonetheless. Then we have in the World War II, we have another example, Mustang P-51, that was a part of the U.S. Army. And then you get to the modern era with F-16, which is a Cold War era. And this is still in use in a lot of countries outside of the United States, of course. Any questions so far? No. Just as an example, the number just like 40 years after the Wright brothers, United States built 96,000 aircraft in just 1 year. And that was for the purpose of World War II, so you would expect a large number of aircraft production. But that's still after the first ever aircraft. We have 96,000 being built in only the United States in 1944. In the whole world, in 1944, we had 240,000 aircraft built. And then in the duration of that decade of war, World War II, the World War II started in 1939, but the production preparation for the war started earlier, of course. So 1935 to 1945, we had nearly 1 million aircraft manufactured in the world. So a very rapid progress after the first flight. And 2/3 of it was created by Allied powers. You guys know who were the Allied powers and who were the Axis powers? Yeah. So, is there any questions about the history? No? Let's talk about the aerodynamics a little bit. What is aerodynamics? The term aerodynamics, Ludwig Prandtl, which is a very important person when it comes to fluid mechanics in general as a field, right? He is like one of the most important people when it comes to fluid mechanics in general and aerodynamics specifically. He defines aerodynamics as something that is used for problems arising from flights and other topics involving the flow of air, specifically air, not any gases, just air. And we have the definition by a dictionary which defines aerodynamics as the dynamics of gases, specifically atmospheric interaction with moving objects. But let's talk about this. What does aerodynamics mean to you? We talked about this part, what do you expect from this part before. But what does aerodynamics mean to you? What do you think aerodynamics is? Or what does it cover outside of airplanes? I mean, we all know aerodynamics is somehow related to airplanes, right? We don't know yet how, but we know it is related. But where else aerodynamics becomes important? Calculating drag force on cars, right? So aerodynamics of cars is actually very, very important when it comes to fuel consumption or the efficiency of the car in general, or any moving object that is moving inside them. Yes, go ahead.
Yeah, I was going to say the same.
What was the solution side? For some reason, I cannot. Yeah, same thing. Exactly. Boats actually are very important as well. That when it comes to boats, is mostly hydrodynamics, because the drag force is there because of water and air. So designing a boat or analyzing a boat, that's something you are interested in, is very complex because you have to calculate the drag force caused by the water as well as the air and the interaction of the two. And you also have an open surface there, which is a nightmare to deal with when it comes to analyzing. What else? What?
I guess like a heat sink with like airflow through it.
Heat sink with airflow on it. Yeah, of course, because you will definitely have some boundary layer generation there, and then the boundary layer is there because of the viscous forces and so on and so forth. Yeah, that's a good example.
Structures generate energy.
Like the what's it called? Wind turbines, right? Exactly. Yes, go ahead. That's yes, exactly. I mean, a spacecraft in general, aerodynamics is going to be very important in the movement of a spacecraft. But the re-entry part is aerodynamics becomes very important. And we will hopefully we'll talk about aerodynamic heating a little bit in this course as well, if you have the time. Go ahead. Exactly. Yeah, so Harun brought up actually two different examples, which both are very important. The flow across bridges, which I'm pretty sure you have heard about the bridge that collapsed because of the vibration over it, right? And you have heard the story many, many times up to now. The aerodynamics, the wind blowing over it is very important. And the force caused by the wind blowing over it and the natural frequency of that whole thing, you should know some aerodynamics to be able to calculate, right? And also the movement of air inside channels, right? That's the other thing. That's actually very important too when it comes to designing an engine or a jet or whatever. It's called internal aerodynamics, that one. Any other examples? Yes. I haven't thought about it actually. So the wind flowing over the cables, right?
Right, yeah, like we have different software to simulate stuff like that.
Exactly. Yeah, that's So aerodynamics is actually used everywhere. Should be utilized in any type of design, not just in airplanes. So that's the point. Aerodynamic is essentially a subcategory of fluid dynamics. As you know, we are going to have three main categories when it comes to the type of fluid that we are dealing with. The first is the hydrodynamics, the flow of water, right? Which you have dealt with in your fluid mechanics course, hopefully, at least an introductory version of it. And then we have the gas dynamics that covers the movement of any gas over any object, then aerodynamics, which is just the flow of air over objects or inside any object. There are, of course, since air is a gas, there are a lot of overlaps between gas dynamics and aerodynamics. But our focus in this course is going to be on aerodynamics, mostly incompressible aerodynamics. If you have the time, then we move on to some compressible aerodynamics as well. But why do we study aerodynamics? The first goal is, of course, to be able to make predictions, do calculations, and understand, to be able to design something or predict the failure of something, we want to calculate force and moments and the interactions of an air with the body in general that will generate the force or the moment. And we also want to be able to understand the heat that is being transferred between the object and the air. But that is mostly, we don't really do heat transfer in this course. And just a little bit, maybe, just a little bit, but the focus is mostly on the force and the moments. And that is essentially the topic of the internal aerodynamics mostly. External aerodynamics mostly. And examples of what we do or what we analyze, what we predict, is like when we predict the generation of lift on an airfoil, drag, moments, or anything on wings, fuselage that is going to help us with the design or the prediction, the failure prediction. And when it comes to heat transfer, the heating of the space reentry is the best example. The combination of heat transfer and aerodynamics, actually, because you're going to get a lot of heating that is happening, and that is actually one of the reasons that they use ceramics in shuttle design, right, instead of aluminum or steel or whatever, right, because of very high temperatures during the reentry. Okay, we talked about the internal aerodynamics a little bit. Internal aerodynamics is mostly focused on determining the characteristics of the flow moving through internal duct, which is usually the topic of another course, namely the propulsion course, which we do offer in this department. So for those of you who are graduate students in aerospace, you may want to take that course with Dr. Farooq as well. You're going to enjoy it. And yeah, any questions so far? Any questions, any comments? What time? Okay, so let's talk about some interesting phenomena that is going to happen that you are going to see when you are mostly focused on aerodynamic analysis. So I'm pretty sure you have seen when these videos where aircraft break the sound barrier, right? And this is what you usually see, right, on the wings, like the water droplets, right, or fog on the wing, right, just for an instant, right? Why do you think that happens? I mean, you have the answer there, but you can think about it for yourself. Any ideas? Like what causes this pressure drop that I mentioned here? Are we clear on about what I'm talking about? Like the idea is when an aircraft breaks the sound barrier or like flies and speeds higher than the speed of sound, or starts flying with the speed higher than the speed of sound, you're going to see a fog on top of the wing. The shock wave is going to create a pressure difference, right? So you're going to have a huge temperature change and pressure change after the shock wave. Who knows what the shock wave is? Of course, you know what the shock wave is, but other than him, who knows what the shock wave is? So 2 people, 3 people, either one of you. Do you want to go? Okay. That's mostly a pressure wave though, right? Okay. What makes it the shock wave? Pardon me? It is essentially a combination of millions or like billions of pressure waves, right? So a pressure wave is a movement of a pressure differential. So before and after the wave, you have a different pressure. When you combine many pressure waves, you're going to get something that's called the shock wave. We're going to talk about shock waves for later on in the course. And before and after a shock wave, you're going to see a huge pressure difference, right? Because it's a combination of a lot of pressure waves, right? And that huge pressure drop is going to cause the condensation, which appears to our eyes like a fog. Does it make sense? So aerodynamic analysis, we're going to see why this happens. We're going to see how this happens. We're going to see the mechanism behind this. Other examples of shock waves or pressure waves, this one here. We see these guns that are firing on USS Iowa. You see the movement of water here, right? This is the pressure wave propagating on the surface of the water. But it doesn't mostly break the water because the surface tension of the water holds the molecules together, okay? So it just pushes the water a little bit. That's the pressure wave you're gonna see. And we also have a huge shock wave here around this aircraft. This is centered in a wind tunnel, but at very high speed. Yes? It does depend on the ambient pressure and the temperature.
It doesn't necessarily mean there's a shock wave.
No, it doesn't. But there has to be a sudden change. You can also see the shock wave generation on cars. It's not just on aircraft. Aerodynamics is present on cars as well. Another phenomena that is actually very people see this phenomena a lot is the wing tip vortices that follows the aircraft essentially, and that is happening because of a phenomenon called downwash on the wing. It essentially means that the higher pressure air is going to move towards from the bottom, from beneath of the wing is going to move to the top, and this is going to cause some vortices when the air leaves the wing, okay? But we're going to talk about all of these phenomena later on in the course. Especially downwash is going to be the topic of one whole chapter. Okay, any questions so far? No? So let's move on to the mathematics of it a little bit. Let's just start with the mathematics. This is just a form. Of course, you have seen all of this before, but we are just, something that I forgot to mention in the introduction part is that I'm gonna mostly use the board. This is one of the few lectures that we're gonna see in PowerPoint because I like using the board a little more than just using a PowerPoint. Using a PowerPoint becomes boring for me, and I assume for you guys as well. So be prepared, I guess. But I will upload the PowerPoint presentations anyway, so you will have access to PowerPoint presentations before the class. So there you are. Let's go back to the topic at hand. We have the most important parameters in fluid mechanics: temperature, pressure, density, dynamic viscosity, kinematic viscosity, and fluid velocity, and the speed of sound, which becomes very important when you are talking about the movement of air on an object, or when you are in aerodynamics in general, when you are doing some aerodynamic analysis, right? These three are related to each other through the equation of state. Rho is equals to P over RT. You have seen this equation of states and all of these parameters many times up until this point. And something that you have to keep in mind is that define pressure in a fluid setting as by this equation. So it's going to be the limit of a very small force, element of force that is being applied on a very small element of area. When you take that limit, when dA goes to 0, you're gonna have the pressure essentially. And we define density as the limit of a very small element of mass divided by a very small element of the volume. Of course, we're talking about the mass of that specific control volume that you are dealing with. Right? But these are only the definitions. I'm not going to ask you to take this limit in any capacity. So you just have to know this. Any questions so far? Just some parameters, nothing specific about this. We have the dynamic viscosity. Let's talk about the dynamic viscosity a little more. Dynamic viscosity is actually something that is going to be, is going to be something that that is very important to us in aerodynamics. It is a measure of fluid resistance to the flow, or it is the internal friction of a moving fluid. But for the first 4 chapters of the book, like first half of the class, we are not going to consider viscosity. We are going to assume that the flow is invisible, okay? which has a lot of implications, but it is actually going to help us do a lot of good analysis and good calculations by making everything a little easier. Okay. But how can we calculate the shear stress near the wall when it comes to a moving liquid? Let's say you are applying this pressure to this top plate. The fluid is going to move inside, right, with a different velocity. And if this plate is fixed, the velocity here is going to be 0. The velocity here is going to be maximum because the fluid molecules are going to stick to the balls, right? And this will essentially cause a shear, a stress that is being applied to the fluid by the wall, or to the wall by the fluid, depending on where you stand. How can we calculate this shear stress? By this very famous equation. Have you guys seen this equation before? Hopefully you have, right? In your fluid mechanics course. Tau, your shear stress near the wall, going to be equal to your viscosity multiplied by the gradient of velocity with respect to y. Okay. Is there anyone who doesn't remember the shear stress equation, or who has not seen the shear stress equation at all? Okay, that's good. That's good. I usually have 1 or 2 people saying that they haven't seen it at all. So, no. But, so as I said, dynamic viscosity in general is going to break the course in 2 parts. So it is a very important parameter when it comes to aerodynamic analysis. So we need to talk about its dependence on other parameters a little bit. The main question you want to answer is this: is your dynamic viscosity, or is your viscosity in general, does it depend on pressure and temperature? And this is something that I want to ask your opinion on. Does it depend on pressure and temperature? This is something that you can think about and have the answer for. All right? As long as you understand what viscosity is, you should be able to answer it without knowing any fluid mechanics or any aerodynamics or any equations. Okay. Okay, that's a correct way of putting it. It definitely, yes, it definitely is strongly dependent on pressure and temperature. And if you think about it, just think about it. Let's say, let's think of gold, molten gold, right? Liquid gold, right? As you increase the temperature, it becomes less viscous, right? You can see that it will move on the surface easier. I mean, I don't think anyone here has seen molten gold, but you can understand what I'm saying, right? You can comprehend what I'm saying, right? So you don't need to go back to any analysis, like any mechanical engineering or aerospace engineering analysis, to be able to understand that the viscosity depends on temperature or pressure. Just by thinking about it, you can see that it is really dependent on pressure and temperature. And there are many, many laws that govern this dependence. One of the most important ones that we are going to see later on in the course is the Sutherland law, that gives you the relationship between the viscosity and the temperature. And it has two constants as well for different situations. Those two constants cover other dependence, other types of dependence of viscosity, to like other parameters. So Sutherland's law tells you that the viscosity is equal to A multiplied by temperature to the power of 1.5 divided by temperature plus B. And A and B are actually Sutherland's constants. But we have these figures as well. They are talking about the dependence of viscosity on pressure and temperature. These lines are isothermal line, which means that on the line itself, the temperature is going to be constant. We have the pressure here on this axis and the viscosity on this axis. You can see as you increase pressure, the viscosity changes on isothermal line. And for different temperatures, you're going to have different velocities. That is also true for different types of material as well. Viscosity is going to be different for different types of material, and its dependence actually on temperature is going to change with changing the material or the substance you're using as well. So it is a complex phenomenon. Viscosity in a fluid is a complex phenomenon that needs to be dealt with a lot of care. And we are going to actually talk about the viscosity, the importance of viscosity, mostly in the second half of the course, some in the first half of the course, but mostly in the second half of the course. Any questions so far? Okay. So this part of the lecture is just going back to what you already have heard, have seen. You don't really need to remember these, but I'm pretty sure, like 99% sure that we have seen this. So something that you really need to start the analysis in fluid mechanics in general, right, is the non-dimensional parameters, right? Who here doesn't know of non-dimensional parameters or dimensionless parameters? Well, let me change the question. Who can tell me what is like one of the most famous dimensionless parameters in fluid mechanics? Reynolds number, right? Reynolds number is a very important and very famous dimensionless parameter that is actually going to be very important and crucial when it comes to the distinguishing different types of flow. It is actually going to help us. Let me actually ask you, what does a low Reynolds number signify? Or what does Reynolds number distinguish in general? What is the classification that can be attributed to Reynolds number? Exactly. So depending on the type of the geometry you have and type of the flow you have, your flow can be turbulent or laminar at a cutoff, a Reynolds number cutoff number, right? Do you remember what's that number for flow on a flat surface? The cutoff number? 5 multiplied by 10 to the power 5, right? 500,000, right? That was the Reynolds number. That's the cutoff use, right? Yeah. And for flow inside the dock, it was 2,300, which tells you that Reynolds number is an important parameter if you want to find out whether your flow is laminar or turbulent. And when you are dealing with air, that distinction is very important. You have to make sure that you know whether the flow is laminar or turbulent. Okay. And something that I forgot to mention is that Reynolds number is essentially the ratio between the inertial forces versus the viscous forces. Lower Reynolds number tells you that the viscous forces are going to be the dominant, which means that you're going to have laminar flow. But higher Reynolds number is going to mean that the inertial forces are going to be dominant, which is going to mean that the inertial forces are actually very turbulent in nature. They are going to make your flow disorganized. That's why you're going to see a lot of mixing and a lot of problems, if you will, in turbulent flow. Is there any questions so far? Let's talk about this other parameter that is going to be very important in aerodynamics, of all things. And then you can go home. What is the speed of sound? That's the first thing you need to define to understand this non-dimensional parameter. The speed of sound is the rate at which infinitesimal disturbances are propagated from their sources into an undisturbed medium. So essentially, it is the rate at which your pressure pulses, pressure waves that are going to move and propagate through air. Speed of sound is a fluid property and is going to depend on the temperature, gamma, which is the ratio of the heat capacity, right? Cp or Cv, and the gas constant. The speed of sound, you can calculate the speed of sound with this equation, the square root of gamma RT. Does anybody remember what was gamma for air from your thermodynamics? Yes, or fluid mechanics. You know what I'm talking about though, right? You have seen this ratio before. Yes? No?
Close to 1.3.
1.4. Usually we use 1.4, right? The gamma for air, we usually use 1.4 unless you are told to calculate it. Because the assumption, we make the assumption that the Cp and Cv don't change with temperature, which is going to mean that your gamma is going to remain constant, is going to remain 1.4. You have the R for air and the temperature. You can find the speed of sound at different temperatures. Okay. So, what is a non-dimensional parameter that is going to use the speed of sound? Of course, it's the very famous Mach number, right? Mach number is the identifier when it comes to aerodynamic analysis, right? You have to define your velocity, your flight velocity, find the speed of sound for that specific temperature, right? To be able to find the Mach number. What is the classification we can get using the Mach number? Does anyone know? Is there a question here? Like the classification that came in with the Reynolds number was whether the flow is turbulent or laminar, right? Or in transition. Subsonic versus supersonic. So Mach number equals to 1 means that your flow is sonic, because the flight is that the speed of sound is the flight velocity is the same as the speed of sound. Lower than a speed of sound is going to be subsonic, and the higher than a speed of sound, Mach numbers higher than 1, is going to be supersonic. We in this course, for the first half of the course, mostly operate at the Mach numbers less than 0.3. So very low speed flights, because we want to deal with incompressible in-between flows, right? And that's where that assumption is true, right? When you increase the Mach number beyond 0.3, you cannot assume your flow is incompressible. We have to do some compressible analysis, which we will get to as well. We will actually talk about hypersonic and supersonic flows too, hopefully, if we have the time. Okay. Any questions? What time is it? Yeah. The clock is 1 hour ahead. What is happening? Okay. Any questions? Okay. So I guess that's it for this class. If you have any questions, send me an email. And from next class, I'm mostly going to use the board. If you have any problem with me using the board, like I guess some people have a weak vision, cannot see the board, just let me know send me an email, and then I can always go back to using the PowerPoints. And that's it. See you on Wednesday.